Okay.
Yeah. All right. Yes, sounds good. Yeah, let's wait 1 or 2 more minutes,
Okay.
and then we can get started. Yeah. Typically, the audience is very, very good. I mean, typically it's more than 70, 80, or more, sometimes more than 100 people attending.
Wow, that's impressive.
Yeah, this is one of those things, right? I mean, in-person seminar, places like Rise, you never get like 100 people attending because the school is the school is like
Right.
like
Right. Right.
four condensed matter experimentalists. I mean, how can they expect 100 people?
Right.
We're like 15, 20 people attending. But now with this Zoom thing, it's really becoming prolific. Yeah.
Yeah.
Good morning, Stefan.
Hey, good morning, Shima. How are you doing?
I'm fine, thanks. How are you?
I'm all right. I'm all right.
Good to see you.
Yeah, it's good seeing you. I haven't seen you guys in a while.
I know.
I guess I haven't seen anyone in a while.
I guess things have become normal now for you guys, or
I mean, lab capacity is sort of getting back there. We have like now 6-foot spacing allowed in labs. Office is still single occupancy, so we have a lot of multi-occupancy student offices, so that's still a hurdle. But yeah, it's getting back there slowly.
Are you guys expected to wear masks and stuff in person, or still that's eliminated?
No, I mean, if you're in your office by yourself, you don't have to wear a mask. But if you're in a space with someone else, then you have to.
I know, yeah, we have to wear a mask when we go to bathroom. I mean, that's
yeah, that's right.
Sort of the situation.
Yeah. I mean, the hope, well, California is supposed to be completely open by like June 15th. So hopefully.
Oh, that's your. Oh, I guess your governor has been recorded, right? I mean,
recalled. Yeah, that's. Well, there's an election, right? Yeah, that's coming up. So.
I see.
That's right.
But he's trying to brag you guys, right? Give you guys money, right? That's all. I mean, I guess you're not eligible, right? You have to have income below a certain amount to get right. $300 rebate from the governor of California, right?
Yeah, I think there's such a large surplus. My understanding is that there's a state like law that if they have a surplus above a certain amount, they have to like give it back to taxpayers. And so this is the one mechanism of doing that, I think.
Okay. Hey, Chimel, you want to say like 1 or 2 words? I mean, before we start.
Yes. Go ahead, Panchang.
Oh, okay. I mean, maybe we can get we have more than 60 attendants. Yeah. So it's a great pleasure to welcome Professor Stephen Wilson from Material Science Department, University of California, Santa Barbara, to give a talk. I invited Stephen because he sort of discovered of this brand new, kagome lattice superconductor. It turns out, I mean, this is one of the newest, right, kagome lattice superconductor, right? Previously, I mean, are there other kagome lattice materials that are known to be superconducting? I mean, maybe there was some, right, many years ago, but this is the newest one with very many anomalous properties. So yeah, so let's welcome Stephen. Please go ahead, Stephen.
Okay, great. Yeah, thank you very much for the introduction, Peng Cheng, and thanks for the invitation to come and talk. And I have to apologize, to Peng Cheng. I kind of like. This seminar started because a member of his group emailed a member of my group whose name is also Stephen, inviting him to talk about some disordered pyrochlore stuff that we were doing. And I just read the email quickly and I was like, sure, yeah, I'll give a talk. And then Peng Cheng graciously, it's like, oh no, why don't we have you give a seminar? And then I had to apologize to my student. And so anyway, we fixed it. But
it's genuine.
Yeah. No, I wanted for you to talk about this stuff anyhow, but the student is more interested in kagome lattice stuff. So
okay.
We both have chances, right? Yeah. Okay.
Great. Okay. So what I want to do is provide an introduction a bit to this material that we've been working on recently, which is it's a kagome metal, and it's a quasi 2-dimensional kagome metal of the form, an alkali metal, vanadium 3 antimony 5. And I'll try and just it'll be largely an experimental snapshot of kind of the current work, because the field there's been a lot of recent experimental work posted, so I'm going to try and capture some of it. So first off, let me acknowledge the people who've done the work, right? So this field has really been led by Brendan Ortiz, a postdoc in my group. And he joined my group from Eric Tober's group at the Colorado School of Mines, where in the waning days of his PhD, he discovered this new kagome material. And so we continued investigating it here at UCSB. And also providing a good deal of the first principles calculation and DFT modeling has been Sam Teicher, who's a student in Ramses Chadri's group here at UCSB. And I'll be presenting a lot of data that's been collected via collaborations that we've been very fortunate to have with people across the world, at a number of different places. For instance, Yusong at Zhejiang University, Jacob Ruff, since all scattering experiments are remote nowadays, has been gracious enough to run a lot of X-ray scattering measurements for us. Mike Graff and Ilya Zeltovich at Boston College. Here at UCSB, we've collaborated closely with Leon Belenz and Ramses Chaudhry group, but also on optical measurements with John Harder's group. Another STM collaboration has been with Zahid Hassan's group at Princeton. And then our photo emission collaboration has been very, very, very nice to work with Junfeng He. And also at Max Planck, we've had optics collaboration with Eke Ukir, and also some transport studies with Maz Ali. And then coupled to Eke's work has been Alexander Serlin. Okay. So first, just an outline of what I'm going to talk to you about is I'm going to try and give an overview of this new system we've been looking at, which is a kagome metal, and I just maybe motivate a bit why studying kagome metals is interesting. And then I'll just try and present the experimental picture of symmetry breaking in these systems. In particular, there's two phase transitions. One is a charge density wave phase transition, which is interesting in of itself. And the second is a low temperature superconducting state, which is potentially unconventional. I think that's not quite established yet, but I'll try and show what's, kind of summarize what I think is known right now. But then also the superconducting state is also interesting because potentially of topological surface states that could interact with it. And then, yeah, so some of the recent measurements I'll be presenting will be some quantum oscillation measurements done by our group, as well as some X-ray scattering. Okay. So just as a quick initial overview, so for those of you who aren't familiar, a kagome lattice is a network of corner sharing triangles. It's named after sort of this Japanese basket weaving technique. And it's long been of interest. In particular, I think, quite a lot of activity has been done looking at the magnetic degree of freedom. Basically, when you decorate a kagome lattice with magnetic moments, and if it's an insulating state, then there's predictions. If if you decorate it with highly quantum moments, you can realize quantum spin liquid states. For instance, Herbert Smithite is an example of this, where people look at the spin excitation spectrum and then realize things like fractionalized spin excitation, spin on continuum. And so a lot of leading candidates for quantum spin liquid phases are rooted in kagome insulators. Also sort of the real space spin textures that you can realize by decorating, if for instance, if the system orders materials like manganese 3 tin, where you can realize effects such as like room temperature anomalous Hall effects, and other interesting spin textures, for instance, on a magnetic lattice that's ordered, but with, for instance, non-collinear spin textures across the kagome lattice. But when one thinks about the electronic degree of freedom, basically in terms of the band structure, kagome lattices also have long been of interest because if you just look at the simple single orbital type binding models, then you get a band structure that has a coexistence of a couple of different interesting features. One being topological physics associated with Dirac points in the spectrum, but also potential correlation, electron-electron correlation physics, because you can realize flat band physics, right? So you can have populate flat bands and potentially promote correlation effects. And so then you could potentially have this interplay between non-trivial electronic topology, but also electron-electron interactions. And there's been a lot of work in this field in recent years, where systems like iron 3 tin 2 or iron tin, or for instance, cobalt 3 tin 2 sulfide or cobalt tin, have sort of started to realize some effects or this interplay between non-trivial electronic states, but also magnetic order associated with sort of the flat band physics of the system. And here I've just summarized a few examples. And then more broadly, if you just look at type binding models of a kagome lattice, and you were to look at the various effects that you can realize at different fillings, there's a long history of predicting different types of electronic instabilities on the kagome lattice. And so here I've just, especially if you start to add electron-electron interactions into the system. So here's just summarizing a few potential charge density wave states or flux phases that can be realized at select fillings. But there's, just to summarize, there's predictions of charge density wave order, bond density wave states, chiral spin density wave states, superconductivity. And what's germane for this talk is our predictions that if you, at select fillings, for instance, at 5 force electrons per band, you can realize saddle points in the band structure at the Fermi level, and these give rise to Van Hove singularities, the nesting between which can drive correlation-driven phases, for instance, charge density wave phases or superconductivity. Okay, and here's an example, a publication which is summarizing that. Okay, so let me introduce the system I'll be talking about, and then we'll first be talking about the charge density wave state in this particular material. So as I mentioned earlier, Brendan Ortiz, as he was finishing his PhD, was looking at this ternary phase diagram between alkali metals, vanadium, and antimony, and he identified a new unreported ternary state of the form AV3sp5. And so here I've shown you the crystal structure for potassium, vanadium, 3 antimony 5. And it's fundamentally, basically, you have a perfect kagome net of vanadium ions, which is coordinated by antimony. And in between these layers, these V3sp5 blocks, is you have a layer of alkali metal ions. Okay, so then you can basically decompose this into different sublattices. One is an antimony 1 sublattice, which is in the kagome plane of the vanadium ions, and the other is basically these sort of graphitic nets of antimony above and below this plane. Okay, and so one thing to note is that this is, the kagome lattice in the system is, is an ideal kagome lattice and remains so down to what the charge density wave ordering temperature in the system, which I'll motivate in a moment. And the other thing to notice is that the vanadium distances are reasonably small, so 2.74 angstroms. And it's, that's comparable to the vanadium distances that you would find in vanadium metal, for instance, right? So this is kind of already hinting that this system, you would have substantial covalency or delocalization effects, and the vanadium ions might be non-magnetic. If you were to just do simple charge counting, then you would, just using conventional kind of ionic rules, you would think that there's maybe 1 free electron per 3 vanadium ions. But however, this system is, as you can tell, because of these close bond distances, is going to be very highly covalent. Okay. So the initial work looking at the electronic structure of this system, this is some DFT modeling that was done on the initial report of the discovery of these materials, basically shows that the electronic structure of these 3 systems are very similar, but there is the Fermi level is predicted to be rather close to saddle points that are located at the M points at the Brillouin zone edges of the system. Okay. All right, so that's sort of an initial motivation that some of the saddle point physics might be operative in these materials. And if you were to look at the systems, so this is experimental data collected on powders of, as I've shown you here, this is for the potassium system, so potassium, vanadium, 3 antimony 5. If you were to look at the transport, you can see it's a metal, but this is transport done on potassium deficient materials, as extracted from powders. For instance, this one has missing 8% of the black line is missing 8% of the potassium sites. The blue line is missing about 15%. So you can see that the low temperature transport is very sensitive to the degree of occupancy on this A site. But then if you look at magnetization, you can see as you cool down, there's an anomaly in magnetization where you see a dip. Okay, so as you cool down, you see the magnetization falls down. And then, so there's a phase transition that you can also resolve in heat capacity around 80 Kelvin for the potassium system. So it turns out this phase transition is present across the series, and it varies from about 80 Kelvin in the potassium system to about 94 Kelvin in the cesium system to about 6 or 110 Kelvin in the rubidium system. Okay, so it's sort of a universal feature across the series. And so I guess some of the initial interest in this system is that Brendan grew single crystals of these materials, which were still somewhat potassium deficient. And so this is potassium, vanadium, 3 antimony 5. And then these crystals were studied by Maz Ali at Max Planck. And what he was able to identify is that there was an extraordinarily large anomalous Hall effect that appeared in these materials. So if you were to put it in this kind of canonical plot of the anomalous Hall conductivity versus the longitudinal conductivity, it sits up here in this region that's typically ascribed to skew scattering. And you can see, we're sitting in the regime that's, above iron, for instance, okay? So it's a very large anomalous Hall effect in this system. And so the initial mystery, this was originally attributed to potential skew scattering from disordered spin clusters, but, in parallel, we were looking at this system with neutron scattering, and we saw really no signatures of magnetism with scattering measurements. And we also gave some powders to our collaborator, Mike Graff at Boston College, and he went and did muon spin relaxation measurements, and basically saw no signatures of electronic moments in the system, basically. So the entire relaxation profile he could model with just weak depolarization, consistent with just depolarization arising from nuclear moments in the sample. Okay, so there's no real local moment electron magnetism that we can find in the system via μSR. So that's a bit of a mystery. Okay, so I'll just add, this is not chronologically correct, but later this anomalous Hall conductivity, the same sort of magnitude was observed in the cesium vanadium 3 antimony 5 system as well. Okay, so it seems to be also a generic feature of the materials. And I'll just add that this is an anomalous Hall, this anomalous Hall effect turns on below this T star or this 80 Kelvin transition that I showed you in potassium vanadium 3 antimony 5. Okay, so it seems to turn on below this phase transition that I described earlier. Okay, so one thing Brenda did was he then really perfected on making stoichiometric single crystals of these materials. And so he basically developed an improved growth and processing technique. And as he did so, he improved the residual resistivity ratio. And so you can get it up to something like 60 to 80, depending on around 60, I think, typically. And then you can look now, this is data collected on a single crystal where we can look at the susceptibility as a function of temperature. You can see in this, sort of cleaner material, the high temperature susceptibility is rather flat, very poly-like. And then you see just kind of a sudden drop as you cool below this T star transition, which is at 94 Kelvin in the cesium system. Consistent with prevents, a gap opening at the Fermi surface, you're losing some density of states in a poly paramagnetic type model. And then again, when in transport, you can see under zero field as the black line, you can see there's this kink in the transport as you cool through this 94 Kelvin phase transition. And then if you were just to do longitudinal magnetoresistance and apply a 9 Tesla field, you can see that there's, I don't have it plotted in terms of percentage, but it's several 100% MR effect that occurs at low temperature. But this, you can see the divergence starts turning on more or less below this 94 Kelvin transition. Okay. And then obviously, so also you also see the anomaly in heat capacity. You see a very sharp anomaly, and this is a very sharp peak, very suggestive of a kind of a first order phase transition. Although we don't see any real hysteresis, but we haven't looked sort of at the, sub half Kelvin type regime. So we haven't looked with very high temperature resolution for the hysteresis. But
so Stephen, what's the understanding of the rather larger increase in stability below 50K?
Yeah, that's a good question. I think initially our picture of that was that there was some just impurity moments somehow in the sample somewhere, very weak. I mean, if you calculate what the kind of fraction of free impurity moments it would be, it'd be very small. However, as I'll present later, there's sort of pictures of potentially that the time reversal symmetry is broken below this charge density wave transition at 94 Kelvin, and it's potentially somehow related to that. We're sort of investigating that now. I think there's more structure to that low temperature susceptibility that you see there. I mean, when we looked a bit more carefully, but that's sort of ongoing. I can't say anything too sharp about that yet. Okay, so structurally, if we look below this T star transition and you were to just, this is again in the cesium system, this is room temperature, structural refinement, and you look at the 10 Kelvin structural refinement. So this is above and below this 94 Kelvin transition. In a powder average structure, you basically see no change, okay? The structure, there's no structural distortion that can be resolved. But if you look very carefully with single crystal synchrotron X-ray diffraction, you find very weak structural superlattice peaks that are 4 to 5 orders weaker than the primary peaks that appear below this T star transition. And I think our initial take on this was it was suggestive of like a secondary coupling to a primary electronic order parameter, something like a CDW, okay? And so, so that was sort of our initial hints that there might be, that combined with the susceptibility data suggests that you might have a charge density wave phase in this system. And then our collaboration with Eke Ukier has also looking at optical signatures of the system. So basically looking above and below this T star transition in both for instance, starting with the cesium system, they can look at the frequency dependent optical conductivity and look at the difference above and below. And what they find is that basically they see spectral wave pushed up, basically consistent with an electronic gap opening. They can fit the onset of this gap, and the optical gap that they can try and fit from their analysis is around almost 80 millielectron volts. And they can do the same exercise with the potassium system, and again they see this sort of spectral signatures of an optical gap opening below this transition temperature. And it's consistent, again, there's still spectral weight below the gap, right? So then it's consistent with a partial gap opening due to the onset of this charge density wave state.
Steve, can I interrupt you for a second?
Yeah, sure.
So from a structural measurement, can you sort of say what kind of distortion that you see?
Yeah, right. That's a great point. We're getting close to doing that, and I'll try and motivate in a moment. Yeah, because of COVID, we can't actually travel to these synchrotrons. And so reliant on people doing these measurements remotely, and these guys get swamped and they have so much data that they can't actually, it takes them forever to provide reduced data for a structural refinement. And so when you start talking about these very weak superlattices that are 4 and 5 orders weaker than the primary, then we have to be very careful in terms of the normalization of the data and the structural refinement. So that's something that's ongoing to try and get a sharp structural refinement. But I'll motivate what we think it is in a few slides. Okay. All right. So another probe of this of the ordering that occurs below T star in these systems is, and a very productive probe has been a number of scanning tunneling microscopy measurements, and I'm just going to highlight a few. So here's from a collaboration with Zahid Hassan's group at Princeton. They looked at the potassium vanadium-3 antimony 5 system, and if they look at the low temperature state, so below this 80 Kelvin transition in that system, what they find is a charge density wave, or they basically see a charge, a texture that appears in the local density of states from their tunneling measurements, consistent with charge density wave order. They can do the Fourier transform of this pattern, and then they see these peaks, which are consistent with what they call a 2x2 reconstruction of the unit cell in the AB plane, which can then be modeled with this so-called 3Q charge density wave ordering, which is sort of a known instability for a kagome lattice. Okay, and then also just as a tunneling spectrum collected below the transition, you can see there's sort of this gap that opens. It's not a complete gap, it's a partial gap. So that's consistent with the optics data from earlier. Although I'll note the magnitude of the gap seems to be different between the two probes. Okay, so but this 3Q order was also observed looking at cesium vanadium-3 antimony 5, right? So this is very beautiful data from Ilya Zeltovich's group, where again, they do the Fourier transform. They can see these 2x2 peaks, which can be attributed to 3Q order due to the charge density wave instability. But then there's an additional charge texture that emerges in this cesium system that as you cool down, there's a charge order that coexists with this 3Q order, which is this sort of unidirectional kind of stripe ordering, okay, which they label sort of this 4A type ordering, which is basically the periodicity is something like 4 lattice constants. Okay. And so I'll talk more about this in a moment, but first I'm going to talk about the 3Q order in this system. Okay, so a bit more in depth, X-ray diffraction measurements that we've done, and this is data collected on the cesium vanadium-3 antimony 5 systems. We can actually look and identify the Q vector associated with the charge density wave superlattice, and this Q vector is indicative of a 3-dimensional charge density wave order. So basically, it's a half-half wave vector in the AB plane, which is consistent with this 2x2 order that the STM people see. But then there's an interplane periodicity as well. So it's basically a half-half quarter for the cesium system. And I'll just mention here that this is the data for the cesium vanadium-3 antimony 5, but for the potassium system, our diffraction measurements are the same for half-half in the plane, but the out-of-plane wave vector seems to be half. So they're more consistent with half-half-half. So there seems to be some difference between the stacking sequence, the size of the unit cell below the CDW transition between the different systems, which suggests that perhaps this interplanar phasing is maybe just some low energy physics that's pretty easily perturbed by whatever alkali metal you put in. Okay, so what are the models for the structural distortion below the charge density wave state? So if you start from an undistorted kagome lattice, then some of the more likely models are you can look at these different distortion modes. There's B3U, B2U, EA, and A1A. And these first three are in-plane wave vectors that if you look at if they're, for instance, minus, 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 this gives you a Star of David structure, okay, which is a well-known reconstruction, I think, from people who've investigated this for a bit for like tantalum disulfide and other systems like this. And so this Star of David structure is shown here. But if you run these 3Q vectors in plane in the reverse, then if you turn to plus, 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 then you get this other structure, which is this what we call the trihexagonal structure. Some people call it the inverse Star of David structure. And then the fourth mode here basically controls the effective displacement of the antimony atoms like out of the plane. So this could give you, this particular mode could give you some interplanar modulation between the orders. Okay, so Sam's DFT calculates that the trihexagonal state should be favored by an order of like 10 millielectron volts per unit cell. This is consistent with some work that was put out at the same time, actually posted before our work. And so again, this type of distortion, so basically, trying to resolve between which is the Star of David, is it realizing a Star of David or a trihexagonal structure was some of our work that we've been doing in the past several months. And so one of the ways of doing this is that the initial photoemission data, when we looked at the electronic structure, sort of failed to resolve a reconstruction of the Fermi surface due to the CDW. And that was because probably the resolution of the measurements wasn't sufficient. So one of the things we tried to do is we looked at quantum oscillation measurements in the form of Shubnikov-Haas oscillations. And so we in particular looked at the cesium vanadium 3 antimony 5 system. And so here, this is just data showing you that we can see Shubnikov-Haas oscillations as a high mobility material, very low electrical resistance. I think, at 2 Kelvin, well, I guess, okay, above the superconducting transition, the rho naught is something like 0.1 microohm centimeters. So you can look at oscillations. This is just looking up to 14 Tesla at 2 Kelvin. You can see they get damped out as a function of temperature. But then if you were to look at just the low temperature data, here's oscillations, and you can see that there's many different frequencies, many different harmonics encoded with this. In fact, if you look at this little box here and then you blow it up, as well as this box here, you can see there's also very high frequency components kind of dressed on top of this lower frequency oscillations. So we can take this spectrum and then we can do the Fourier transform, and I'm going to break it up into 2 different windows. So this window here I'll call the low frequency window, and this window here I'll call the high frequency window. So in the low frequency window, we can identify 4 sort of clear frequencies. So the alpha, which I label as alpha, beta, gamma, and delta, which map to the frequencies, kind of eyeballing frequencies by eye here. So they're kind of real frequencies that we can identify in the data. And the same thing with the high frequency window. In this case, we can identify 5 high frequencies, which again, as a consistency check, you can kind of eyeball them in the data. So these high frequency components get rapidly damped out as you heat up the sample. So we can't really track the sort of the power spectrum as a function of temperature, but the low frequency orbits we can. And if we do that, then these low frequency orbits basically, if you fit to, as a function of temperature, you can basically back out an effective mass. And so they're all about 1/10 of a free electron mass. So it's very light electrons, consistent with perhaps their origin being from sort of the Dirac points sort of near the vanadium, due to the vanadium orbitals in the system. Okay. So one of the things we tried to do was we tried to identify what frequencies are coming from what. There's a lot of, the Fermi surface is pretty complicated. There's a lot of bands. And so what we first did was look at sort of the undistorted Fermi surface. So this is the high temperature state. And Sam Teicher did some very beautiful analysis of calculating what the extremal orbits would be, which they occur in the k=0 and k=½ plane. And so if you just do an analysis of the extremal orbits that would be sensitive to in the quantum oscillation measurements, first of all, just note that there's 2 frequencies that we just aren't in our experimental resolution. They're too large. Okay, but then there's if we count all the remaining frequencies that should be within our experimental resolution, then our data basically sees 3 extra frequencies in the low frequency region and 1 extra frequency in what I call the high frequency region. Okay. So that's consistent. We expect that there should be some reconstruction of the Fermi surface as we cool below the CDW state, but this was just a kind of an initial check. Okay. And so then what Sam did was he calculated the Fermi surface in the candidate distorted phases. So in the Star of David state, as well as in the trihexagonal state. And so here I'm just going to show you what the surface looks like in the trihexagonal state relative to the undistorted phase. And so the key difference is that as you cool into the trihexagonal state, you gain a number of induced vanadium-based orbits, right, due to the reconstruction of the Fermi surface. As you gain that both in the k = 0 plane, but you also gain 1 in the k = ½ plane. Okay, so in that case, what we can do is we can just kind of qualitatively match the number of orbits we should expect to see in each frequency window versus the candidate structure Star of David or the trihexagonal. And so that's what we can do here. And if we look here, what I've shown you here is just basically the Fermi level, which can be adjusted plus or minus relative to what the experimental value is. This experimental value was determined, was benchmarked to STM and ARPA's data on our samples from the same batch, which is consistent with one another. And so if you look at the Fermi level that from the experiments, basically, and you can count the frequencies that arise, this is just showing you on the left panel the frequencies that you expect from the undistorted structure, right? And then this is the one that we know there's deficiencies in terms of the high frequency, in terms of 1 missing high frequency orbit, but obviously 3 missing in the low frequency regime. And then we can calculate what the frequencies would be expected in the Star of David and trihexagonal structures, which are shown here. And so basically this shaded box here at the bottom is just the resolution of the calculation that Sam's doing, meaning he can't really identify from his unfolded band structures orbits below this frequency threshold. So if we do that, then only the trihexagonal state really matches the 5 frequencies in the high frequency regime. But it also, both the Star of David and trihexagonal do predict an enhanced, additional frequencies in the low frequency regime. But only the trihexagonal really matches in this high frequency regime. So in that particular model is the only one that's qualitatively consistent with the quantum oscillation data. Furthermore, we can identify from these models that the bands that are basically not bands, the orbits that we observe at low frequency that change are due to reconstructed vanadium orbitals, which are endemic to the Kagome lattice. So basically, this is just sort of the first experimental insight that the charge density wave state is being driven via the vanadium orbitals in the Kagome lattice. And so kind of supports the use of some of these, I would say, more minimal models, looking at just sort of the physics inherent to a Kagome lattice, driving some of the interesting properties of these systems. Okay. And so more recently, John Harder's group here at UCSB has done some transient reflectivity measurements where they looked at a larger unit cell than we did. Basically, they looked at a 2 by 2 by 2 unit cell. And then they looked at the transient reflectivity. So they basically looked at the reflectance as a function of time after being hit with a pump, sorry. And so what they see is that there's some phonon modes that turn on as you cool below the CDW transition in here, and they can do a symmetry analysis of these phonon modes based off their DFT models. And then they can ascribe that the most likely explanation is what they call this MLL state, which is the trihexagonal structure in the plane, but then out of the plane, basically it's shifted from one plane to the next, basically. So each plane of the system has a trihexagonal distortion, but basically it's just shifted in the plane one to the next because there's sort of one Q vector that wins out of this 3Q order. Okay. All right, so some of the interest in this charge density wave state, other than the details of whatever the structure it is that follows, is that some of the initial STM results suggested there's a potential for time reversal symmetry breaking due to the charge density wave phase itself, meaning it has an imaginary component in it. You can think of it as like an orbital current of some sort. And the initial report of this was from Zihita San's group, where what they did was they looked at these 2 by 2 peaks in the Fourier transformed STM data, but then they looked at the 3Q vectors comprising this, and they basically looked and they saw that there is a difference in the intensities, basically when they look at the Fourier spectrum. And they defined a winding going from the lowest to the highest peaks in this distribution of these 3Q peaks. And so basically they defined some type of winding. What they found is that they could actually switch the distribution of this intensity by switching a magnetic field. So basically they saw that which Q peaks were favored in the 3Q order was coupled to magnetic field. Okay. And so then they've since identified this in the rubidium system as well. And I think I saw a paper last night, but I haven't read it in detail. I think also in the cesium system. So this for this particular technique, in this particular method of analysis, there seems to be some changes that are induced in the charge density wave state seen locally via STM when you apply a magnetic field. So I want to add here that it's not universally agreed. For instance, there's another work on potassium vanadium-3 antimony 5 that doesn't see this type of magnetic effect. And I think that's something that's going to get worked out, in the coming months, probably. I think the claim is that, it's not a sample effect because we provided samples to both groups. So it's the same samples. It's just however the STM is preparing the surface might make a difference, or I think in some cases, some people are concerned about tip effects in this particular measurement. Okay, so as another kind of hint that there might be some time reversal symmetry breaking below the CDW, in the same paper from Zahida-san's group on the potassium system, they also looked at μSR, and I think they looked at transverse relaxation rates. And so it's a very subtle effect. So basically, as they cool down, they can see a jump in the transverse relaxation rate under magnetic field, obviously, because they're applying, sorry, I'm sorry, I want to say this correctly. It's relaxation rate under transverse magnetic field. Okay, so it's kind of like, it makes the muons oscillate, and then they look at the relaxation rate as they oscillate on cooling. Okay, and so basically they see a jump in this relaxation rate as you cool below this, and this is under an applied field of a couple Tesla. Okay, so it's maybe hinting that there is some type of coupling below the CDW. In isolation, maybe it's not too profound, but coupled to the STM data, it's maybe a nice kind of supporting piece of information. Okay, so then looking at lower temperatures, initially reported in the cesium system by Ilya Zeltovich's group, is this sort of quasi one-dimensional 4A component of the CDW order. Okay. And so this, again, as I mentioned, sits on top of this 3Q order, okay? And it turns on below a lower temperature scale, so below about 60 Kelvin. And there's no real sharp thermodynamic signatures, for instance, in susceptibility or heat capacity for this. So it'd be somewhat of a crossover, basically, if it's a bulk effect. It's also been seen in the rubidium system more recently. And I think my understanding is in the potassium system, STM sees it less frequently. Okay, maybe there's certain select regions where you can see it, but it's perhaps not as stable of an effect in the potassium system. And so I know that the STM groups perhaps are debating whether or not it's a bulk or surface effect, basically this charge modulation. I personally think that there are signatures that it is indeed a bulk effect, or it's a signature of something going on in the bulk, meaning if you look, this is again these sort of transient optical reflectivity measurements from John Harder's group. These are the phonon modes that this phonon mode in particular analyzing below the CDW, but you can see there's sort of this broad spectral weight, a component of the oscillations that turns on below the same temperature of 60 Kelvin in the cesium vanadium-3 antimony 5 system. Okay, so there's certainly some sort of bulk response that's turning on in the lattice spectrum of these systems below the same temperature scale in which you see these quasi one-dimensional or you see these one-dimensional charge modulations turn on. So I think this is supportive of a bulk effect. And another potential piece of experimental evidence supporting this being a bulk effect is some very nice work from Haihu Wen's group, where they're looking at basically they're looking at transport along the c-axis, but then they rotate a magnetic field within the AB plane. So it's a transverse magnetoresistance measurement, and they look at the anisotropy of that as you cool down. And so basically what they find is there's some C3 symmetry breaking as you cool below 60 Kelvin or so in the cesium vanadium-3 antimony 5 system, which is also kind of supporting of some type of, maybe unidirection, some pneumatic type of correlations forming.
Hey, Stephen, so I mean, does the Raman scattering measurement, I mean, suggest that you have a new optical phonon mode at 3 terahertz? Is that the story?
Right, that's a good question. Yeah, so yeah, I guess I didn't mention there is a Raman paper where they also see the same effect in Raman. This is basically time domain Raman, and he's just Fourier transforming it, right? This is transient reflectivity. But yes, Raman sees the same thing, and so I think in both cases it would mean there's some sort of broad, there should be some broad optical mode, I guess, if it's coming from a lattice component. Yeah, maybe like a very short lifetime kind of optical response, yeah. Okay, so if you look at even lower temperatures in these systems, then as you know, I've already mentioned at the beginning, is that the systems were found to be superconductors. And so this is a discovery Brendan made, was reported last year, is that, you know, basically the superconductivity was missed earlier because of the deficiency on the alkali site, right? So if you really make these things stoichiometric, then you can stabilize a superconducting state. It was originally reported in the cesium system and has a TC of about 2.5 Kelvin or so. The transition in resistance is broad. That might be something that's intrinsic to the material. We originally thought it was because we were driving too much current through it, because it's such a good metal. We wanted to have some reasonable data, and our bridge isn't that great. But this might actually be something that's intrinsic to the zero pressure state of the material. And okay, so we saw this originally in the cesium system, and then Brendan also managed to perfect the potassium system and also saw that it became a superconductor below about 1 Kelvin. And since then, it was also been identified in the rubidium system, which is also a superconducting state around 0.9 Kelvin. Okay. So looking at the superconducting state, there's a lot of ongoing work on that. And I would say that there's not a lot of consensus about the nature of the superconducting state yet. I mean, I think probably consensus is in the following. You know, if you look at the magnitude of the specific heat jump due to this onset of superconductivity, it's sort of below what you consider the BCS type of typical BCS model. You know, basically, if you're to look at the magnitude normalized by the Sommerfeld coefficient times the TC, it deviates from the expectations of weak coupling BCS. But at the same time, STM is able to resolve the superconducting gap, and it's roughly about 0.5 millivolt. So, you know, if you look at sort of the 2 delta over kBTC for these systems, it's on the order of, it's like 5 or 6. So it's kind of like strong-ish coupling, you know, moderately strong coupling, however you want to try and, how you want to try and describe it. But the, you know, the combination of these two things would suggest that you either have an anisotropic gap function or a multi-band gap, you know, so more than one gap. And there's a lot of experiments underway. I'll just highlight two, just to kind of highlight some of the things that are being discussed. For instance, there's thermal transport measurements that are suggesting that you have a nodal superconducting state in the system. There's other parallel measurements on tunnel diode oscillator measurements that suggest that you have something more like an isotropic gap in the system. And this is stuff that's being worked out now, and I don't think there's a clear consensus on that yet. But what you can do is you can look at the normal state electronic structure of the system, and this is some work that Sam Teicher did, and you can just try and do a topological classification of the normal state metal. And if you do so, then you can identify sort of a continuous direct gap across the system, and you can identify, and you can, by looking at the parity of all the bands at the time reversal invariant momenta, you can identify the system as a Z2 topological metal, which means that it should have topologically protected surface states. And Sam was able to do this classification and identify surface states reasonably close to the Fermi level at the endpoints, okay? And I'll show that on the next slide. And then here is the initial photo emission measurements on cesium vanadium 3 antimony 5 done by Junfeng He. And basically just benchmarking the photo emission data to the DFT calculations done by Sam Teicher, basically showing that DFT agrees very well with the observed band structure. And again, the DFT model was shifted, kind of a rigid shift to match the experimental Fermi level. Okay, so if you look at the surface state spectrum and you calculate it, so Sam was able to identify surface states that are reasonably close to the endpoint, reasonably close to the Fermi level at the endpoint, so about 50 millielectron volts above. And so more recent work by Junfeng He's group has very beautiful ARPAS data where they actually show that if you heat the system up to like 200 Kelvin, they can start to populate states above the Fermi level, and they can see these surface states. And then what they do is they cool below the CDW transition, and what they find is that actually the way that the system, the way the band gaps change as you cool below the CDW, it actually pushes these topological surface states down to the Fermi level, which is kind of, you know, it's really exciting, right? Because that means that you have topological surface states that are at the Fermi level as the system becomes a superconducting state, okay? So the topological surface state should be participating in some way in the conduction as you cool through TC. And so that's of interest to communities interested in the topological superconductivity, for instance, or, you know, for instance, this proximity induced topological superconductivity via like a Foucault type of model. Okay, so then looking at the superconductivity a bit more deeply, there's been a number of nice work, primarily I'll just say, I think this work's coming out of China, looking at high pressure measurements, looking at the interplay between the charge density wave state and superconductivity. So here is an example of some measurements done by Yusong and at Zhejiang University, where you have potassium, vanadium 3, antimony 5, and you apply pressure. And what they find is by tracking the transport anomaly, basically in resistivity of the CDW transition in the system, they can find that the CDW is suppressed. And as the CDW is suppressed, the TC goes up. It goes up to about 3 Kelvin. And then after the CDW is completely suppressed, they see sort of this large flat region where the CDW is not, where the superconductivity doesn't care much as you go up to 2.5 GPa. And this is more or less consistent with like a conventional picture of, closing the charge density wave gap and then providing more density of states for your superconducting state, and then you can have a higher TC. So that's kind of a conventional picture. But then sort of other work looking at higher pressures, this has been done basically looking up now to 40 GPa. What they find is that the superconductivity comes down, I think potentially goes away, but then it comes back with a second dome here at higher pressures, okay? And so there's some open questions about whether or not this superconducting phase at low pressure is the same as the superconducting phase at high pressure. And that's sort of a subject of ongoing investigation. And then the details even become kind of more intricate as you look at that was the potassium system. You instead look at the cesium system and you look at sort of details in this low pressure regime. So this is some very nice work showing like what they call a double superconducting dome, meaning they start to suppress superconductivity. They start to suppress, sorry, this is the charge density wave state. They start to suppress the charge density wave state. They see superconductivity, the TC goes up in the cesium system, and then it starts to go down, and then it comes back up, and then it goes down again and sort of flattens out in the low pressure regime. And so you sort of have this, in the low pressure regimes, these sort of two peaks in the dome, which is potentially suggestive of unconventional superconductivity or some unusual phase competition going on in this regime. Again, in the cesium system, similar to the potassium system and also the rubidium system, as you look at even higher pressures, right? So this is going, this ends at 7, right? So if I now look and pick up here, basically TC kind of recovers and has again the sort of higher temperature, this higher pressure superconducting phase, which might be distinct from the low pressure one. So there's some very nice X-ray diffraction measurements that were done recently by Alexander Serlin and Eke Ukir, where they looked at, this is data on the cesium system. And what they find is that as you apply pressure and you start to traverse this, this phase diagram and you approach sort of this 20 GPa type of second superconducting dome, a couple of things happen, right? So one is that the C-axis sort of continually decreases in a big way. So you have a very anisotropic compression as you apply pressure. Okay, and so you can see this is a big change. This is normalized to 1, right? So the ambient value is 1. And so you have basically a 20% decrease in the C-axis lattice parameter by the time you hit 20 GPa. It's not sharp like the things you see in like iron pnictides, like the lattice collapse phase. It's not like a first order transition or something, but it is kind of interesting that you have this really large anisotropic compression. And then so basically by refining the structure under pressure, what they find is that as you reach this 20 GPa phase, they find that basically these antimony sites get much closer together, and you start to have strong antimony hopping in this direction in their DFT models. Okay, and then the other effect they can see is by looking at the Fermi surface of their DFT models, they find that as you transition potentially from one superconducting state to the other, they find that there's an antimony derived PZ pocket that basically comes and goes, basically vanishes around the crossover where superconductivity is purported to completely vanish under high pressure, and then it reemerges in the second superconducting regime, the SC2 regime. Okay, so kind of running out of time, so I just want to just highlight a few things. There's been a lot of theoretical work that's been coming out looking at these systems as well. I won't highlight it all. I'll just mention that there's been some very nice theoretical analysis looking at trying to analyze the idea of time reversal symmetry charge density wave state in these particular materials. And so there's been proposals for a couple of different type of flux states that could emerge, that could generate this anomalous Hall effect, by breaking time reversal symmetry, would be derived from basically nesting born from the saddle points of these systems. There's also, and so similar to this, Leon Valence's group here at UCSB has been looking at the types of charge density wave states that you can realize from this 3Q order, doing sort of a Landau analysis, renormalization group theory. And basically, again, there's two saddle points near the Fermi level and their DFT models. And there's some very nice, work looking at the different possibilities of, having a real charge density wave state versus an imaginary charge density wave state that can break time reversal symmetry. I think in their analysis, the leading instability is the real charge density wave order, but it's something that could potentially be activated, like where an imaginary component could be turned on via the application of a magnetic field. Studies looking at the superconducting state, there's been some nice work looking at the analysis of electron-phonon coupling strength. And I think the outcome for this was they suggested that electron-phonon coupling strength isn't enough to account for the TC that's reported. So suggests maybe you have unconventional superconductivity. And similarly, 3-band type binding analysis with RPA also suggests that you might have unconventional superconductivity, for instance, like F-wave pairing. But this is all sort of ongoing stuff. I think the superconducting state's not very well defined yet. And so I probably in this talk I've missed some works, but there's been quite a lot of papers, so I couldn't hit them all. But it's it's an exciting field, basically looking, where you have sort of a lot of techniques can start to talk to these systems and hopefully form some coherent picture. STM, ARPAs, and there's been some recent NMR studies, optical reflectivity, high pressure studies, and obviously magnetotransport and some ongoing penetration depth measurements. And so I think it's an interesting field. So I'll just summarize what I think are the kind of interesting aspects of these systems. So, they're a new class of kagome superconductors, and I think what maybe sets them apart from there's of a previous, I think, lanthanum ruthenium silicon kagome system was a superconductor, is these guys are quasi two-dimensional. So they're more they're sort of the more intrinsic to the kagome type of like two-dimensional physics. They seemingly have an interplay of non-trivial electronic topology. There's Z2 metals, and the surface states seem to be pushed down to the Fermi level as they go through TC, through the superconducting transition. And they also seem to have a charge density wave instability that's linked to the onset of a strong anomalous Hall effect. And I think going forward, they're an exciting platform because they're very exfoliable. And so they're kind of amenable to a number of different device architectures and experiments. I think the superconducting state, it's potentially unconventional superconductivity. I think that's an ongoing study. And I think people are excited by the potential that you could have these nested endpoints due to the Van Hoff singularities, and that's sort of long been predicted to give rise to some unconventional superconducting mechanisms. For instance, like chiral D wave was one proposal from a long time ago. I would say the superconducting state, I think it's probably more solid that it's likely multi-gap or non-S wave, one or the other. There's been some STM studies that I didn't have a chance to highlight here, that there seems to be some interplay between the superfluid and this pneumatic order and this 3Q order, basically suggesting that you could have this sort of pair density wave state. And then, so looking more solidly at the charge density wave state, I think the pictures, the experimental picture sort of coalescing along the distortion being in the plane being this trihexagonal distortion. But it's a three-dimensional structure, superlattice. And so understanding what drives this three-dimensionality is an ongoing investigation. And obviously the big question is, does the charge density wave state really break time reversal symmetry? And I think there's a lot of probes looking to identify that now. And so with that, I'll stop and I'll thank you very much for your attention.
Thank you, Stephen. Yeah, such a nice talk. Yeah. So questions? Maybe I'll ask you first. So has NMR measurement showed that whether there's susceptibility drop below TC? Are there people identify NMR measurement on this?
Yes. Yeah. I think they do see the sort of night shift. Yeah, they do. Yeah.
So it's more likely to be singlet.
Yeah, I would say from the experimental picture that I've been able to digest, it's more likely singlet. I don't know what you expect with like F wave. Do you expect? I don't know the particular expectations for that, but yeah, I think from the NMR data, I believe that you do see the shift below TC.
Okay, thank you. Yeah.
You also see a Hubble sector peak below
okay.
TC.
But that's probably a signature of BCS, right? Isn't it?
Well, it would be a signature of, I mean, that would be suppressed with, nodal structures and things like that.
I see, but you see clear peak, I mean, a TS, but that's typically for BCS superconductor, you see that, right? For D wave, you don't, right?
Yeah, right. That's
right.
That's what I just said. Yeah.
Okay. Yeah, Pavel? Yeah.
Just a question about the energy scales. Has the CDW gap been seen in ARPAS? And how far are the Van Hoff singularities from the Fermi surface? What does the experiment tell us?
Yeah, that's a great question. So there is recent ARPAS work that actually can see the CDW gap by, I think, Ricardo Coming. That's been posted where they can look at basically the momentum space anisotropy of the CDW gap. So that's been mapped in detail now. The Van Hoff singularities, to my knowledge, are like right at EF. Like, I mean, all these because there's so many bands and things move so fast as you kind of change the Fermi level in your models, right? So as best we can tell, they're sort of right there. So, say plus or minus, like, I don't know, 10 millivolts or something. I mean, they're kind of right there.
Thank you.
Okay, Henry?
Hello?
Yeah, please.
Yes. It seems from all what you say that this system is really weakly correlated. I just want to publicize the work that we have been doing on sodium cobalt 8, in which there is an underlying cobalt kagome sublattice, which is highly correlated and which is a very good metal, but not a superconductor. So I think there is a big, we are speaking of kagome lattices, which can be very different depending of the strength of correlations. I know that our work is absolutely unknown, but
Are you talking about the water-doped sodium cobaltate? Or
no, sodium cobaltate dry without water. And at a given sodium content, which is X equal 2/3, we get an ordered state in which the order of the sodium eliminates some of the cobalts because they become 3d6 and then they are non-magnetic, which means that, and the remaining cobalts are in a kagome structure. So this splits the cobalt plane, which is triangular, into a cobalt sublattice, which is kagome, and a central cobalt 3+, which is below the Fermi level in some sense field. And the interest, I think the big difference with this kind of system is that in the cobaltine and in this vanadium, you still have vanadium site. You still have here it's antimony sites which are in the triangular complementary sites of the kagome.
Okay.
So it seems to me that I don't know in the band structure calculation whether you can see that, which is the role of these antimony sites.
I mean, yeah. So I mean, the primary band structure. I mean, so basically, if you do an orbital projection, basically at EF, the things primarily come from the vanadium orbitals here. So here you go. Yeah. So this is sort of the orbital projection. And there is some mixing. There's a little bit of mixing from the antimony sites as well. But yeah.
So the question is, what is that leading to the situation which is less correlated, or is it mainly because the vanadium is? It would be nice to see whether you have a cobalt equivalent to the.
Well, I mean, I think in sodium cobaltate, right? The cobalt ions they're not nearly as close as what we're talking about, these vanadium ions, right? I mean, this is really like a metal. Like, I mean, this is a true,
It's true that the big difference is that in the cobaltates you have its oxides, so you have a bridging between the cobalt oxygen. So the distances with the between the cobalts are probably larger, and we are nearer from a mod situation in some sense.
Can I jump in on this? So maybe question
okay.
just on the same point. Sorry. For Stephen, I guess, is there some information from RPS on velocity renormalization, and for Henry, is there some indication in cobaltates on charge density wave?
Well, in the cobaltates, unfortunately we cannot do RPS in the ordered state. You see, the situation is the kagome is a peculiar phase which is obtained only for sodium equal to 2/3. You cannot change the sodium content, so you have to lock the order. And to get a surface which is ordered is something which seems to be hard for RPS experiments. One needs to do RPS in the bulk in that case.
Right.
But we are fighting for quantum oscillations and stuff like that. We are hoping to get information through other tools. STM and RPS are not going to be the best tools in that case. But we them are, and we have a lot of information on the magnetic properties on the local scale.
Jaime, you have a question?
Yes. On the original anomalous Hall effect paper, where they attribute the large anomalous Hall effect to some spin clusters, it looks like now maybe people are going more towards some time reversal symmetry breaking state from the charge density wave to explain this. I'm wondering if people have done the transport across the CDW transition.
Yeah, you mean looking at just electron transport across the CDW?
The anomalous Hall effect across it.
Yeah, I'm sure people have, right? I mean, I don't.
I think he's looked at the magnitude of that. I personally haven't done it, but I'm sure it's in Maz's paper, Maz Ali's paper.
Okay. Yeah, I just okay. It was just low temperature.
Oh, was it? Okay.
Yeah.
Okay. Yeah, it might be. There might be some challenges to doing that, right? Since it's a multi-band system, I'm just trying to figure out. As someone who hasn't tried it, I can't tell you what the challenges definitely are, but there might be some challenges trying to get that high.
Okay. All right. Thank you.
Tong, you have a question?
Yes, I have a question. Maybe the day before yesterday, there was a paper posted on arXiv, and it shows that there's a twist in the magnetization data at 5K. So 5K is already non-superconducting, and there's something happens. So my question is there maybe a different phase in the HT phase diagram, or what is going on if you apply the magnetic field?
Okay, so I guess I haven't seen this paper, but your question is, do we see any signatures of when you apply a magnetic field, you see a change in the magnetization below 5K? That's the question?
Yes.
I don't think we've isolated anything like that. I'm not going to say that it's not there. I mean, I think exploring the magnetization more deeply below the CDW transition, I think there is some structure to some of the features there that could be real. So I could say that's possible. We haven't identified it.
Actually, Stephen, I mean, does your magnetization data consistent with the heat capacity data? Also, your heat capacity data seems to have an upturn at low temperature. I mean, you suggested that the stability data seem to sink, due to some sort of impurity. But your heat capacity data also shows a small, upturn, right, at lower temperature. So,
let me see if I can see.
in your heat capacity data, right? I briefly saw it. Yeah. Low temperature heat capacity. I mean,
low temperature. Okay.
Yeah. I saw a figure somewhere.
Yeah, I think we were sort of describing that to like a Schottky anomaly, right? I think that's a nuclear Schottky. I think that's kind of
Is
what
that, is that consistent with the fact that the magnetization also goes up? I mean, what sort of magnetic impurity you might think is, in there? It's a single crystal, right?
Yeah, I know, but like, yeah, it's a single crystal, but they're not very magnetic, So, squid, you can see, everything. I don't know. Typically, if you really want to rule if it's intrinsic or not, you have to do this very laborious exercise of touching everything with plastic tweezers and making sure you don't have any type of impurities in any of your source materials and all this stuff. It can be very hard. Yeah. So I guess we haven't done that yet.
Okay. I'm sorry, Chmiel, yeah.
Thanks. So Stephen, like you said earlier that in the quantum oscillations, you can fit it with entirely vanadium states, so the various frequencies you had. But then you seem to suggest that there's also antimony p states that come into play. I wonder.
Oh, sorry. Yeah. I mean, I guess maybe I said that wrong. So the idea is the vanadium states are the ones that change. So we still see oscillations from the antimony p states. Yeah. Let's see which ones we see. Yeah.
Okay.
They're sort of labeled here.
Thanks. Now, for the D states, is there some information about the velocity renormalization compared to the DFT, or?
Masses are so weak.
That's a good question. I don't know off the top of my head. I think if it's there, it would be in the sort of latest work by the latest photo emission work, I think, that can see the changes due to the CDW gapping, the anisotropic gapping of the surface. They can probably start to look at velocity renormalizations, but I don't know the numbers off the top of my head.
Okay, thanks.
Okay, are there any other questions for Stephen?
I wanted to ask one more question.
Oh, okay, sorry, I saw you're done. Okay,
Yeah.
okay, go ahead.
Can you say something about the evolution of the anisotropy, let's say of resistivity or maybe other properties too, with respect, to C-axis? This seems to be quite a two-dimensional material. So the question is like, how does CDW affect the anisotropies? Also,
Right.
You mentioned at some point that there could be in-plane anisotropy. I wonder if that's seen anywhere except for STM, this kind of peaks and so on.
Okay, yeah. So the in-plane anisotropy, I think the evidence isn't, or the proposed stuff is from, this is transport along the C-axis, but they apply, but basically all they're doing is they're rotating the magnetic field in the AB plane. So I think they're claiming that there's some in-plane anisotropy that they're picking up by doing this. And sort of we've done similar measurements, and we do see some anisotropy on our crystals as well that turns on at low temperatures. Some sort of C3 symmetry breaking. In terms of transport anisotropy as a function of temperature, the data we have, let me see. I didn't see a major difference. Let's see. Let me see if I can pull it up here. So, oh, I don't have it in this talk. Okay. Yeah, I don't have the slide, but basically, if we collect the resistance, the resistivity, let's say, if we check just the conventional electrical resistivity as a function of temperature along the C-axis, and then overplot that with the resistance along the in the AB plane, then they kind of map. One is about between 300 and 600 times more larger than the other, but the ratio doesn't really change as a function of temperature, as far as we can tell.
And is there a strong magnetoresistance also for fields applied in plane? Because I believe this strong magnetoresistance you talked about is mostly for field along C-axis, right? So is there any big effect if you apply in-plane field?
Yeah, it's weaker when you apply the in-plane field. There's still a little bit of MR, but it's much weaker than along C.
Okay, thank you.
Okay.
Can I also ask a question?
Okay.
You mentioned that there may be time reversal Brock symmetry at charge density. What are specific options? What are possibilities? And what are experimental indications for one or the other? How to discriminate between different types of T-Brock?
Oh, okay. How to discriminate?
What are the options of T-Brock and how to discriminate them experimentally?
Right. Okay. So I think there's a number of different, and then these are just some of the recent ones, right? I mean, looking at this particular material set, different types of sort of flux phases, I guess, for this charge density wave. So here's the references. I think there's a lot of previous work looking at kagome lattices also, and there is some previous work, I think, looking also predicting that you could get some type of flux phase on the kagome. The experimental evidence right now is, there's no momentum resolved, I think, in terms of scattering type of measurements that could maybe distinguish between these. I think the experimental evidence currently is just founded in the STM data that sees some type of dominant Q vectors that switch in the 3Q order as you switch the direction of the magnetic field. I think that's one drive. And then the other is, well, there's this mu-SR data that suggests that maybe something is happening magnetically because you see a jump in the relaxation rate in a transverse field type of measurement. And then I think.
But these experiments, do they allow to discriminate between different options, which you just present? You present several different options.
No.
How to discriminate between those? Not just to prove that there is T broken, but just to.
No, there's
to
no.
have more detailed information.
Yeah. I mean, more detailed information. I mean, one could imagine trying to do like a really high resolution polarized neutron experiment, right? Trying to look for this and trying to look, at scattering. That hasn't been done. Other options, to the best of my knowledge, the neutron scattering would be a good way to try and like compare predicted structure factors for these different phases, perhaps.
Not done yet.
That's not done yet, no.
Okay. Yeah. Ozu-Chen, you have a question?
Yes. Hi. Very nice talk, by the way. I have two questions. The first one is about the origin of these charge density waves. Is this phonon driven? Is this correlation driven? What do we know about the origin of what drives these charge density waves? And the second question is about, earlier in the talk, you said you have these like two different measurements on the powders and the single crystals. And then you said there's not much structural deformation on the powders as opposed to single crystals. So what does that tell us? What do we learn from this about this charge density wave, say? Okay,
cool. Okay, so they're somewhat maybe linked questions. So I'll tackle the second one first. So you don't see the distortion in the powders simply because the superlattice peaks as probed by X-ray scattering, synchrotron X-ray scattering, are too weak. So they're 5 orders to 4 orders weaker than the primary peaks, and with powder averaging, you just miss them. And so you need single crystal diffraction even at a synchrotron to see it. And then so that couples into your other question, meaning what drives it. So certainly the lattice distortion that we see is driven by electron phonon coupling. I think there's DFT, I think, and some other models have really identified that. Now, whether or not that's a secondary order parameter of some primary electronic instability, I think is not established yet. And I think that requires some like careful order parameter analysis in my mind. I think there's some other ways to try and dig it out. So we're sort of working on that.
Okay, thank you.
Okay, I mean, it seems like there's no more. Are there any other questions? Yeah, if not, I mean, let's really appreciate Stephen for this wonderful talk. Yeah, thank you, Stephen.
Great. Thanks, everybody.
Yeah.
Thanks, Stephen.
Thanks, Stephen.
Thanks, Stephen.